Mr. Morris was like, what are they talking about? A higher
I
curve?
get it now.
Hey.
Give him like
One
a fake lecture.
One of the most important things I can teach you all year, this year, is this right here on the board. Not this. Sophic thought that he had to add something. In any reaction, bonds are breaking and then new bonds are forming. Bond breaking
I think I have a better
in
view,
chemistry
just saying.
is always associated with an addition of energy.
doing it.
You need to add heat or energy to break bonds. Write this down and highlight it. When bonds are formed, energy is always given off.
Oh. That's like the total opposite side. I was just like boom, and it was like taken off.
Yeah, it's not though. It's not. In order to get that breakage, energy must be put in. This is 100% always true for every single reaction. The bond's breaking requires energy. The bond formation gives off energy. So that's what this bond energy table is going to tell us. Okay.
Wait, I thought it was the case that, like, if you were trying to break, for instance, like a double bond of nitrogen or whatever, you have to take in energy to break the bond, but then when it actually breaks, it releases energy into the atmosphere, and then to rebuild it.
Just the breaking of the bonds is that it requires an intake of energy. If nothing else is made, then that was a very endothermic process. But a lot of times bonds will break and then something new forms, and that new formation of something gives off the energy.
Okay.
But yeah, just breaking the bonds, you have to put energy into it. Now, on page 382, or 362, I'm sorry, 362, we have this table. The title of the table is Average Bond Energy. You should also know this as bond dissociation energy. Notice all the values on here are positive values. These values are how much energy it takes to break each of these bonds. So the first one up there, a hydrogen to hydrogen bond, it takes 432 kilojoules of energy to break a mole of hydrogen bond. Wow. So look at what it says up here. This is kilojoules per mole. So if you have a mole of hydrogen, you need to add 432 kilojoules of energy to break all the hydrogens apart for one another. Carbon-to-carbon bond is not quite as strong. It's 347 kilojoules of energy. Notice this though. The single carbon-carbon bond is 347. What do you expect about the double carbon-carbon bond? It takes more energy because there's two bonds on there. It's over here. Almost twice as much energy to break a double bond between carbons. And then a triple bond, it takes 839 kilojoules of energy. So anyway, that's how you read this thing. This is telling how much energy is required to break these bonds. Now, what about forming bonds? What about if two H's are coming together to make an H2 molecule? Well, it's the same amount of energy, but with a negative sign in front of it. So if you're going to make a carbon-carbon bond, it would give off 347 kilojoules of energy. Okay? Now, I have an example for you. If we're making ammonia, N2 plus 3 H2s yields 2 NH3. How much energy is involved in this change? Now, we could find the delta H for this reaction by looking up on that heat of formation table and taking products minus reactants. That's one way you can find delta H. But you can also find it with this table. Because in order to make ammonia, you've got to break the N's apart and break the H's apart, and then they rearrange to make these new bonds. How much energy is involved? Do you know what the N bond is in N2? Is it a single, double, or triple bond? Do you know that one?
Double.
No, it's a triple bond. It's a triple bond between the N's. And by the way, on the test, I would probably not make you do dot structures. I would make either the structures very obvious or tell you what the bond is between. So you're not taking 5 minutes writing dot structures on a H2, that can only be a single bond, but there's 3 of them. Notice the thing is balanced. So it needs 3 H's to break apart. So in order to even try to make NH3, you've got to break that bond and break 3 of these bonds.
Wow.
Yeah?
That's a lot of energy.
How much energy does that take? Well, let's add it up. Nitrogen, the N triple bond N bond is 941. This one, there's 3 of them to break, and that energy is 432. So it's 3 times 432. Now this molecule, there's 2 of them. How many NH bonds are formed? No, 6.
6.
3 there and 3 there in the balanced equation. So the NH bond is on top of the second column, 391 times 6. Oh, I forget something here? These bonds are being formed. This is a negative value. Yeah. So that's where I say the total energy, the delta H for this thing, is going to be the total of the energy involved in breaking the bonds. That plus that. And if somebody would do me a favor and multiply that up, 941 plus 3 times 432, and then that's going to be all added together plus this negative value of the bond formation. 6 times negative 392, I can't remember, this is negative 23 something.
I got -109.
Overall, right?
Yes.
Did you get this value? Take 6 times negative 391.
It's like 2,300 something.
2, 3, 4, 6.
4, 6. Okay, yeah, so you've got, this is the breaking bonds in the reactants. This is the formation of bonds. I'll say forming, or formed, in the products. This is always going to be negative. So that's why I have that equation as the heat of the, the energy involved in breaking the bonds plus the energy involved in forming the bonds, because I know that's going to be a negative value. So really you are subtracting. It's a little confusing. I didn't want to put a negative sign in there because then I had people saying, well, you have to subtract a negative number and make it positive. No, just add the 2 together, but that number is always going to be negative.
It's like absolute value.
It is, yeah, it is kind of. Yep. All right, so this is another way to find a delta H. So the answer to this thing, the delta H of this would be that minus that, which is positive, I'm sorry, negative 109
Really?
kilojoules.
Okay.
Are we good?
Last thing, no, almost good.
Oh my god.
Is it negative 109?
Those are 2 ways that we can find, theoretically, what delta H is. Then, we also need to find experimentally delta H. The experimental determination of delta H, you can actually make measurements and see if you can determine a delta H. That's what we'll be doing in the lab on Friday and Monday, is we'll be trying to determine a delta H for a reaction. Now this is kind of silly, cracks me up really. The first law of thermodynamics was, defined by physicists a long time ago, and that was the whole amount of energy in the universe is constant. And then we had the second law of thermodynamics. We'll talk about that in chapter 17. There's a third law of thermodynamics. But then scientists realized when they were doing calorimetry, which is this, really there's another law of thermodynamics that belongs first as a foundational law. They already had the first law identified
So
though.
they named it the 0 law.
So this one comes before the first. That's why it's called the 0th law.
What? I thought that was the actual name.
Like Zeroth law, thermodynamics.
Man, that guy's cool. Oh no, it's the 0th law.
Yeah, I know, but the other ones already have their names. Spencer?
I have a picture for this.
Yes?
Yeah, I just found it yesterday on Facebook.
Okay, we'll take a look. While Spencer's looking that up, the 0th law of thermodynamics says this. When you put 2 things together at different temperatures, the thing that was warmer is going to give some of its energy to the thing that was cooler. So the warm thing is going to give away some of its energy, its temperature is going to go down. The cool thing is going to take some of the other one's energy and it's going to increase. That exchange will continue until they come to equilibrium, which means the same final temperature. Same final temperature means that one is not higher in energy than the other, and they're not going to be able to exchange energy. Sorry. So that is what the zeroth law of thermodynamics says.
That's so stupid.
That says that the energy gained equals negative the energy lost, really.
I thought zero
Let's see that
was.
thing.
It's kind of the law, but like not really.
Can you turn this off now? Yeah, thanks.